Introduction. Stoichiometry in plain Google search is defined as the relationship between the relative quantities of substances taking part in a reaction or forming a compound, typically a ratio of whole integers. This points out that stoichiometry has something to do with the formation of a compound. Thus, in order to define the stoichiometric compound, we can consider the compound in which the reactant or constituent elements of the compound are in integer numbers. It is usually proposed that stoichiometry follows the law of conservation of mass, where the total mass of the reactant element is equal to the total mass of the product, thus leading us to believe that the relations among quantities of reactants and products typically form a ratio of positive integers. This means that if the amounts of the separate reactants are known, then the amount of the product can be calculated. If we take the example of water, the chemical formula of which is H2O, thus the total mass of water molecule is the sum of the mass of 2 hydrogen atoms and 1 oxygen atom. Here, 2 molecules of hydrogen react with 1 molecule of oxygen gas to yield 2 molecules of water. This particular chemical equation is an example of complete reaction. Stoichiometry measures these quantitative relationships and is used to determine the amount of products and reactants that are produced or needed in a given reaction. Defining quantitative relationships among substances as they participate in chemical reactions is known as reaction stoichiometry. In the example above, reaction stoichiometry measures the relationship between hydrogen and oxygen as they react to water. We can further define that stoichiometric compounds are those compounds which maintain their stoichiometry or simply maintain the ratio in which they were formed. Here we must understand that stoichiometric compounds can still possess the defects which are termed as intrinsic point defects. As displayed in, some of the well-known defects are called Schottky, originating due to cation and anion vacancies, anti-Schottky, due to cation and anion interstitials, Frankel, cation vacancies and interstitials, anti-Frankel, anion vacancies and interstitials, and anti-site defects, originating because of cation and anion swap. A two-dimensional arrangement of atoms to describe non-stoichiometry. Upon the aforementioned analogy, we can describe the non-stoichiometric compound as antithesis of stoichiometric compounds. Thus we can describe non-stoichiometric compounds as chemical compounds, having elemental composition whose proportions cannot be represented by integers. Most often, in such materials, some small percentage of atoms are missing, or too many atoms are packed into an otherwise perfect lattice work. In order to define non-stoichiometry microscopically, a situation of array of atom, shown by the open circle in two-dimensional primitive cubic crystal can be imagined. In such scenario, the absence of the atom from the regular place will form vacancy, described as I, displacement of the atom will create Frankel pair, described as 2, and substitution of the atom by another smaller or larger atom, shown by closed circle, can be referred as non-stoichiometry. Nikolai Semenovich Kurnikov along with his students has worked quite significantly on stoichiometry. Kurnikov et al. Suggested that the non-stoichiometric compound could be allocated in the categories of berthollides and daltonides depending upon the monotonicity in property and composition correlation. The term berthollide was recognized by the International Union of Pure and Applied Chemistry, IPAC. The name berthollide was formed from combination of two well-known chemists of 19th century, Claude-Louis Berthollet and John Dalton, who proposed the substance composition theories, albeit these theories were in opposite direction, and later Dalton's theory, law of definite proportions, prevailed with significant exceptions.